And the swag this week, the game is going to be Magic the Gathering, which is a card game, but the stuff that we're doing here, the sort of principles that I'm talking about, could apply to many different games. There are lots of games with a similar mechanic of like deck building games where you have a deck and you cycle through your cards and then and you can discard and draw and that kind of thing. So the specific example I'm using is Magic, but again, a lot of this applies to many different games as well. No, it is... I don't know what that means. Okay. Yes, if there's anyone who wants to sponsor this video, no, don't. Please don't. Okay, so it's just a very simplified version of the rules. You have 60 cards in your deck, and your deck can contain up to 4 copies of any particular card. So you can have multiple copies of the same card in your deck, and you draw 7 cards. Every turn you draw a card, except for the first turn you start with 7. And if you have a land card, you can play it, and you can attack or cast spells, which costs mana, which your land cards give you, basically. So you want to have enough land so that you can cast the spells and do the attacks that you want to do, but you don't want too much land because you don't want to clutter up your deck with all of these land cards and not have enough attacks or spells or creatures or whatever. And then you can discard down to 7 cards. So, just starting off very simple, let's find the probability of drawing one particular card in your first turn. So if you only have 1 copy of the card, then that's fairly easy. The probability you get it on the first turn is just going to be, well, on the first turn, you want 1... Oops, sorry, I'll get myself a little marker here. There's 1 way to get that card, because there's only 1 of it. And then you want 6 of the other 59 cards in the deck. And that's divided then by 60 to 7, because that's the total number of opening hands. Because you're drawing a hand of cards without replacement, and you don't care about the order. So remember those 2 questions. Can you get the same object twice? In this case, no. Each of the cards are distinct. And do you care about the order? In this case, also no. So we know that we're using combinations here. So the probability of getting it on the first turn is 1 to get that card, 59 to 6 ways to fill in the other 6 cards in your hand, divided by 60 to 7. And then that ends up just being about 11.67%. So 7 over 60-ish. Also, you could think about this logically. So you can have sort of a logical explanation rather than a combinatorial explanation. Every card individually in the deck has a 1 in 60 chance to come up because there are 60 cards, and you get 7 draws. So the chance that you get the exact card that you're looking for is going to be 7 over 60. We could do the same thing to find the probability of getting it by the second turn, by the third turn, by the fourth turn, etc. And as you can see, that probability goes up linearly with time. If there's only 1 copy of the card, then the more times you draw, the higher the probability that you will get it by that turn. And it's a linear function. But more interestingly, what if we have more than 1 copy of the card? Let's say you have 2 copies of the card in your deck, then we really are asking about the probability of getting at least 1 of it on turn 1. And in probability, whenever you're asking a question involving at least 1, it's usually easier to work with the complement, the opposite of that event, which would be not getting any of that particular card. So here it's going to be easier to calculate that by taking 1 minus the probability of not getting any of that card on the first turn. And that's going to be 1 minus... if we're not going to get that particular card, we need to choose all 7 cards from the 58 remaining cards that are not the 2 cards, the 2 copies of the card that you want. Again, divided by 60, choose 7. And that gives us about 22%. So just slightly less than twice as much as if you only had 1 copy of the card. We can do the same argument to get at least 1 of that card that you're looking for by turn 2, at least 1 of the card that you're looking for by turn 3, etc. We can get all of those probabilities by just taking 1 minus the probability of not getting any of the card that we want. And in this case, if we have 2 copies of the card, there's 58 cards that are not that one in your deck. Finally, if you had 4 copies, the maximum that you can possibly have, we can calculate those same probabilities as well. And then with that, I just sort of made a table here of all of these probabilities. So the probability of getting at least 1 copy of a card that you have 4 of on your first turn is just about 40%. So pretty good. The probability of getting at least 1 copy of it by turn 2 is 44%. etc. And I've just put those values in the table just so you can see. By the time you get to 4 turns, you have a over 50% chance of getting at least one of that particular card that you have 4 copies of. So how can we actually use this to build a deck that's sort of optimal that we want to play with? One thing that's important, as I mentioned when I was explaining the rules, is that you want to have, again, enough land cards because they provide mana to cast spells, but you don't want to have too many because that takes up space from other cards that we could have, right? We're limited to 60 cards maximum in the deck, so we don't want to have tons and tons and tons of land because then we won't be able to have enough other good cards. So there's sort of this balance that we want to strike between having enough but not too much. So we can use this sort of calculations that we've done before to think about what would be the optimal number, optimization, love it. Think about the optimal number of land cards to put into a deck. So let's just, without loss of generality, we'll call the number of land cards N, capital N, and we're going to assume for now that it's at least 4. It's not 4 copies of the same land card. Land is a sort of category of cards, so we can have more than 4. They're just different different land cards. So we'll have N land cards in your deck of 60, and then of course that means there are 60 minus N non-land cards. And what's the probability of getting at least 4 land cards in your first 4 turns? That's sort of like a reasonable amount of something that would be a good idea to have. So it's not the only thing we care about, but it would be a good idea to have at least 4 land cards drawn by the end of your 4th turn. That's sort of a good benchmark. So we can calculate that probability. We want the probability of at least 4 land cards by turn 4, which is, by turn 4, that would have been 10 cards that you've drawn total. And again, it's easier to calculate this as the probability of 1 minus 0, 1, 2, or 3 land cards. It's just a little faster to do the calculation that way. So again, we're using the complement of the event. Well, probability of no land cards is really easy, because if we want no land cards, that means all 10 of the cards that we draw on our first 10 draws, so first 4 turns, have to be non-land. So we have 60 choose N, 60 minus N choose 10 for the number of ways that we could do that. We could draw 10 cards that are non-land over 60 choose 10. So that's pretty easy. The probability of 1 land is a little bit trickier. So what we want to do is think about how we can build that in like a sort of a chapter 3 problem. We want to have exactly 1 of the N land cards, and we need exactly 9 of the non-land cards. So 9 of the 60 minus N non-land cards. And there's going to be N choose 1 times 60 minus N choose 9 ways to do that. So making sure that we do calculate exactly. What we could not do, what would be incorrect, is to say, well, we want 1 of our N land cards, so there's N ways to do that. And then the other 9 cards can be anything. So then it's just 60 or 59, I guess, choose 9. That would be wrong, because that will double count any cases where you get more than 1 land card. Whenever you're looking at sort of like there's multiple categories of objects and you're looking at getting a specific number of one type, you have to specify the specific number of that type and that the rest of them are the other type, because otherwise you run the risk of double counting. So overall, that probability is this here. So N choose 1 to get the 1 land card, 60 minus N choose 9 to get the other non-land cards, and that'll be over 60 choose 10. We can do the same thing for 2 and 3. Again, sort of 2 land cards and 8 non-land, 3 land cards and 7 non-land, and add those all up and divide it all by 60 over 10. So in the end, we get this huge, hideous expression, yuck. It's all a function of N, though, capital N, the number of land cards in your deck. So altogether, this big ugly expression is the probability of getting at least 4 land cards by turn 4, which is a sort of a good, reasonable starting goal for a game. So it's not a nice looking function, but rather than try to like optimize it with calculus or anything, we could just calculate what those values are for different values of N. So I did that, and I just put it on a graph for you here. The probability of drawing 4 or more land cards in 4 turns, and then here on the x-axis is the number of land cards in the deck. That was what we call N. And on the y-axis here, we have the probability that we calculated up here, this ugly expression. It's just I just plugged it into Excel. It's pretty straightforward. So this is really neat. This tells us that based on how many land cards we have in our deck, the probability of drawing 4 or more land cards in the first 4 turns is not a linear function. It's I don't even know. I mean, it's probably some kind of factorial, but whatever. It's a increasing function, but it's not strictly increasing. So what you can do is decide your own tolerance. You can decide your goal. If you want to have, say, an 80% chance of meeting that goal of having at least 4 land cards in your first 4 turns, you go here, you find 80 on the graph here, and that looks like about 28 or 29 land cards in your deck will do it, and the rest non-land. If you want to be a bit riskier, if you're okay with taking a chance that you don't have 4 land cards in your first 4 turns, then you could go down even lower. So if you go to about 65, then 24 or 25 land cards in your deck will be enough. If you want to be super careful and you want like a 95% chance of getting enough land, then you would go up to here, wherever 95 is, probably somewhere around 30, 36, or 37 land cards. So you can pick your own sort of risk tolerance for how likely you want to be to have enough land in your deck in the first 4 turns, and then design your deck as follows. So choose the number of cards that fits with your desired probability of having enough. All right, so that's all I wanted to say about this. Again, this idea of figuring out how to build a deck to satisfy whatever conditions you like. You can apply this to lots of other games or lots of other aspects of this particular game, but the principle is always the same. When we're talking about drawing hands from a deck of cards, we're using combinations because we can't get the same object twice, and we do care about the order. And then using those tricks of making sure sometimes it's easier to work with the complement of an event, and making sure that if you're looking for a certain number of a particular type, you also have to specify how many of the other type there are to get a probability calculated correctly. All right, that's it for the swag today. Are there any questions from the folks watching? I'm going to check Piazza too, because I put a post there for people to comment on if they don't happen to have a Twitch stream, or a Twitch account, I mean. Nobody has commented yet, but that's okay. So any questions, thoughts? Does anyone here play Magic? It's kind of an old game, but... Or if you know other games that work similarly that you recommend, you can put them in the chat as well. I'm always looking for new games to play. Alrighty, don't see any questions. If some come in, again, if you think of something, feel free to type away anytime you like. For now, I'm going to move over to my machine learning idea of the week. Oh, there we go. It is. There it is. Oh, good old-fashioned poker. Right. Yeah. So poker is another fabulous application of combinations. Yeah. I said I would post a link to a poker hand calculator last week, and I forgot, so I will try and remember to do it this week. Bug me if I don't. Yeah, they're all just based on, no pun intended. They're all, the foundation of all of them is combinations. Okay, so for this week's machine learning idea, I just wanted to talk about the difference between supervised and unsupervised learning. You always, it's not like, you just like let a robot out into the wild and let it walk around and completely unsupervised and then it takes over the world. Like, not that kind of unsupervised learning. The difference is very specific, and it has to do with whether you essentially provide the algorithm that you're doing or that you're using with some labeled data to start with. Oh, is Pandemic, the board game, also probability based? Most definitely, yes. Yeah. Oh, that's such a good idea. I'm going to add that to my list of games to maybe talk about in the future. Yeah, because you can sort of, if you've never played the game, it's amazing. Particularly appropriate these days. It's a great game. Yeah. One of my friends wrote the app for it. It's a really, he did a great job with the app too. But yeah, it's a really good game, and there's definitely some probability. You don't get to design the deck in that way, but you could think about like what's the probability of having an epidemic in the game. So just making it very clear I'm talking about the game within the next few turns, and then that can guide your strategy. So if you have, if you need to do something or you want to do something within the next 2 turns or 3 turns, and you can think about how likely is it to get an epidemic before it comes around to your turn again, when the setup of the initial deck is slightly random. So how that works, oh, this is so cool. I'm just pause my machine learning for a second. So how it works is you take the number of epidemic cards that you're going to be using. The beginner game, you start with 4. I think the more advanced game, you have 6 or maybe even 7. You divide the deck up into that many chunks, and then you shuffle 1 epidemic card into each of them. So it's actually not truly random. It's random within each, say, quarter of the deck where that card will appear, but it's not the same as just taking 4 epidemic cards and shuffling them into the deck. True randomness would be, like the game would be much weirder. This way, you're sort of guaranteed to have exactly 1 epidemic somewhere in the first quarter of the game, and exactly 1 somewhere within the second quarter of the game, etc., etc. So it's deliberately non-random, but then within each quarter, it's random where that card ends up. So you can do some calculations based on that. Fabulous idea. Awesome. Okay, so back to machine learning. Sorry for that digression. Great question. The idea with supervised learning, again, is that the algorithm is provided with labeled data. So it's provided with a set of data that has, the characteristics. So whether that's, the size of the tumor, or like the characteristics of a house, or the characteristics of a message that you're trying to classify as spam or not. And then as well as those characteristics, what category it belongs into, or what the final price of the house was. So you have both the characteristics and the response that you're trying to model on some of that data. So you give the algorithm all this data, labeled data, so what the characteristics were along with what type it was, or what the final numerical result should be, and then it tries to build rules based on those characteristics and those final provided values. And then a good algorithm will also sort of test whether it works on new data rather than just fitting the existing data very well, because even if it fits the existing data very well, that doesn't necessarily mean it will predict other stuff well. Unsupervised learning, on the other hand, you definitely give it some data to start with, but the data is unlabeled. So you don't know, or the algorithm doesn't know, and neither do you, whether what the correct category would be, or what the correct price would be for the house, or something like that. So an example of that would be, here's some information about, or here's some images, try to classify them into groups. Or here's some customer data, so the data of the spending habits of different customers. Try to cluster them into different groups based on these characteristics. Like, we don't know what the categories are, we don't even know how many categories we want, you figure it out. So then the algorithm will look for similarities in those characteristics and then group them together. It can also be used, unsupervised learning can also be used for sort of dimensionality reduction. So if you think about analyzing a genome or something, there's hundreds of thousands, possibly millions of pieces of information, and that's just too much to work with. So exploratory data analysis like that is an unsupervised process where it will sort of look at the different characteristics and see if it can reduce the dimensionality. So maybe instead of needing 100 things, it can only use one thing to sort of summarize a bunch of information. So it reduces the number of characteristics from millions down to a number that's usable. So that's kind of the idea. So supervised learning, you're given some information about the characteristics and the answers for those characteristics and use it to build rules to extrapolate to new data. Unsupervised, you don't know what the answers are. You're sort of letting it explore the data and maybe cluster them or reduce the dimension of the data. And someone has posted some excellent links there. Maybe I've seen those, I'm not sure, but I definitely will check those out, and they sound good, so I'll post those links on Piazza as well. So if you want to learn more about both supervised and unsupervised learning, that is something you can do. All right. That was pretty short, that one, because I didn't have anything specific. Someone posted on Piazza something about the naive Bayes classifier, which is what I'm going to be talking about next week. So that's what I've got for week 3, because that's where we're going to learn Bayes' rule next week. And that's kind of the basis of a lot of machine learning classification algorithms. So we'll definitely check that out next time. But with that, I think I'm done this part. And now I would like to open it up for questions. What is the probability that I'll end up a machine learning researcher? I mean, if you're conditional on you being in Waterloo math, probably reasonably high. In the general population, it's not that high, but this is a biased sample that's listening to this stream right now. There is a great website. I think it's called willmyjobbereplacedbyarobot.com or something like that. I remember looking that up. Professor is pretty low on the list. I think there's only like a 23% chance that my job will be replaced by a robot within the next. I don't know how it's calculated. It's probably some silly thing happening behind the scenes. Oh, that's a great question. What is the probability that I answer every item on every quiz randomly and manage to pass the class? You know what? I think I'm going to calculate that, because so there's some interesting things. So pass, do you mean a 50 to be able to go on to Stat 231? Or do you mean a 60 so that you can actually do proper stats courses? There's a lot of machine learning courses you need those 3rd level stats courses for, just letting you know. Should we aim for a 60? Aim for a 60. Okay. So, each quiz. Oh, this is going to be harder than I thought. Well, let's just talk about a single quiz. So, single quiz. Let's get I didn't have this on yet. So, quiz. There's going to be 10 questions. And you guys probably remember better than I do how many of them were multiple choice and how many of them were just put in a random answer or put in a numerical answer. They're not all multiple choice. They're not all multiple choice. Let's say half of them are multiple choice. Ooh, no, that's going to be really tough. 4 were multiple choice? Oof, okay. It's going to be really hard if you're answering like straight up randomly. Should we like, go away from reality for a second and imagine that they're all multiple choice? Let's do that. Let's say imagine, I know they're not, but suppose they're all 5 option multiple choice. I know they're not, so this is a simplifying assumption. Then the probability of getting the maximum score out of 3 attempts at least being 60. Oh, this is such a cool question. Okay, so instead, let's look at what's the probability of getting at least 60 on 1 attempt, and then we'll see how we can take that number and then see if what's the probability of getting at least 60 on the maximum of 3 attempts. So for 1 attempt, the probability of, I guess, 6 or more, so greater than or equal to 6 correct, is, okay, if we want to have exactly 6 correct, that would be, each one has a probability 1/5 of being correct. Oh yeah, we're assuming that there's 5 options for each multiple choice. So we would need 1/5 getting correct to the power of 6. And then we also would need 4/5 to the power of 4, right? So that would be the probability of getting the first 6 correct and the next 4 wrong. But we actually can order them in any order we like, right? Like we don't need to get the first 6 correct and then the last 4 incorrect. It could be any other combination. So if there's 10 questions, how many ways are there to pick which questions you get right and which questions you get wrong? Think about that for a second. There's 10 questions and you want to choose which 6 you get right. How many ways would there be to do that? If you want to type it in. Yes, we're assuming there's only 1 correct answer per question. It's not like one of those multiple select. Yeah. Agree, yeah. We could say that anything that isn't multiple choice is just automatically a 0, but then it's going to make it pretty much impossible to pass. So I was ignoring that. Okay. So yeah, for now, we're just starting with exactly 60, and then we'll add the other cases. Yes, someone said it. 10 choose 6. Yes, you got it. So 10 choose 6, because we're going to figure out which of the 10 questions we get right. There's 10 choose 6 ways to do that. So that would be exactly 6 correct, but as you very correctly said, we do need at least 60%. So we also have to include the possibility of getting 7 or 8 or 9 or 10. So we'll have 10 choose 7, 1/5 to the 7, 4/5 to the 3, and then 10 choose 8, 1/5 to the 8, 4/5 to the 2, and then 10 choose 9, which is just 10, 1/5 to the 9, 4/5 to the 1. And then finally, if the genius that you are, guessing randomly for all the questions and ending up with 10 out of 10, that has a probability of 1/5 to the 10. There's an invisible 10 choose 10 and an invisible 4/5 to the 0 there, but that's what you get. So I'm going to just go pop over to Excel real quick here for a second. All together, that probability is, oh folks, it's not looking good for our intrepid heroes. The probability is 0.00637. Yikes. Okay. So dang is right. Well, hold on though, that's just one attempt, but we want the maximum of 3 attempts. So basically we get 3 tries at this, and then, so the probability of getting, I guess, right, let's do it. So for 3 attempts, all we need is to get one of them above 60 and we're happy, right? And this is a case, right, if you get at least 1 attempt over 60, you're happy. So here it's easier to work with the complement. You could take 1 minus the probability of all below 60. And assuming that your attempts are independent, which is also incorrect, hopefully if you do poorly on the first one, then you study and then you do better on the next one, yeah, it's going to be 1 minus 1 minus 0.00637 raised to the power of 3, and that 0.01899. So I'll just call it 0.019. So just about a 2% chance of passing a single Mobius quiz, or rather not passing, but getting at least 60. If you completely answer randomly. So this is, again, I like the advice, yeah, just study. I think that's sage advice there. All right. I'm just sort of looking. Okay. So yeah, let's, hopefully that answers your question. I don't think it was a serious question, or maybe it was, but that was some fun probability that we got to do. And all of it just using the stuff that we know from chapter 3 and a little bit of chapter 4. Again, assuming that's a 2% chance of passing each one. And then if you want to pass the overall course, you have to do that a bunch. And then don't forget, we were assuming they're all multiple choice, but they're not. So if you answer the numerical questions randomly, you're going to have basically 0 chance of getting those ones right. So I would strongly recommend studying just for that reason. Okay, let's, there a bunch of new questions have come in. So let me see if I can summarize that. Someone says good enough for me. Okay, so the question was, for quiz 1 question, based on past experience, it seems there is a 6% chance that someone will be injured during the construction of this apartment building. Which statement best describes the method to determine the probability? Why is the answer not subjective or does not fit any of our definitions? I think the key word, someone's got the answer there. It's based on past experience. So based on some data, it's sort of looking at a history, and there's a large, hopefully representative amount of data in the past of constructing buildings that under similar conditions. So one of the relative frequency ideas is that if we repeat it under similar conditions, what's the frequency with which it happens? So that's why I would say that this one most closely fits the relative frequency definition, because we have, again, a large amount of past data. It's kind of like the difference between what's the probability you get into a car accident in this year, and that's probably closer to subjective, whereas what is the probability that a randomly selected university student gets into a car accident this year? That would be based on like a large collection of data, and that's kind of a lot about how insurance works. Actually, they sort of look at trends over time, try and have data that's representative of the population they're trying to model, and then use that to estimate probabilities of future. So that's using sort of a frequentist approach, or the relative frequency definition. But can't the word experience be ambiguous? I mean, a little bit. Like, based on past experience, that implies like that there is data, I guess, not just like one person's thought. Like subjective is where you really have nothing to go on but your gut instinct, I guess. That's kind of the idea of subjective. More clear to mention, based on past K trials, this result occurs. Yeah, I agree. That might have been clearer. Cool, great question. How many attempts would it take to make a reasonable chance of passing the course if you take it multiple times? So that's a nice question as well. Let me see, can I scroll down here? I can, a little bit. I only have a tiny bit more room, and then I'll just have to erase everything. So yeah, I guess like you could think about find n such that the probability of passing after n attempts is at least you know, however many, whatever, greater than 50% chance. How about that? Find n such that this like 1 minus 0.00637 to the n is at least 50%. That's kind of the question you're asking, right? Like, how many attempts would you need to have at least a 50% chance of getting over 60 or higher, I suppose, on this Mobius quiz? Aha, 109. And it's 109. Yeah, right. If you're using you would need 3 attempts 37 times, or 109 attempts. Oh no, not factorial. Sorry, I'm just excited. Not factorial. 109 attempts at a quiz if you're guessing randomly every time, and if there's 5 options for each one, to get a more than 50% chance of getting your maximum grade above 60. Oof, that's a lot of qualifiers. But basically, study, do it. You're not going to guess randomly. You're going to pass the course by guessing randomly. How many quizzes are there? Yeah, you would be pretty old by then. I suppose you would. Yeah, don't guess randomly. Don't try to. I mean, if you want to for your first attempt, go for it. But honestly, don't. Just don't waste your time. Study and remember, they are open book. Like the tests are, the quizzes are, you're allowed to consult the notes. You're allowed to look at anything that's on the Learn site or even anything on Piazza. Just please don't like Google questions or ask other people, but you're welcome to use the resources that are available to you if you're not sure. And you have 90 minutes to do it. So for 10 questions, that's 9 minutes each. I can do that math in my head. Then you'd want to sort of, on average, take 9 minutes per question at the most. And so if you feel like you want to look something up, do it. Yeah, like don't just try to guess. Like see if you can look it up, because you do have the time to do that. Yes, there are 6 Mobius quizzes. Oh, okay. This is a new question. How would the quiz question change? Oh yeah, the one that we've been talking about. If we wanted the overall quiz grade for all 6 quizzes to be greater than 60%. That is a really great question. That is a bit more complicated than the tools that we have to deal with right now. What we would need for that is random variables, which is what we're going to talk about in chapter 5. So basically we would say the score that you get on each quiz is a random variable. And in fact, it's a binomial random variable, if you've heard of that. And then we would look at the sum of those 6 binomial random variables. And that's, even that is pretty complicated. So we would look, the sum of independent random variables is known as a convolution. And so we would have to find some way to get the sum of those binomial random variables. So we could do it, and we'll have the tools to do it once we finish chapter 5. So maybe we can revisit this question then. And that's a really great question, because it's not that each one needs to be above 60. It's that the overall average needs to be above 60, which means that over the sum of all 6 quizzes, if there's 10 questions each, that's 60 questions overall, we need at least, what's 60% of 60? 36? 36 questions, right, over all of those. So yeah, we could do it. We could do it that way. Thanks for asking. That's a neat extension. And yeah, once we have random variables as a tool, that will make this question even easier to explain and understand. So we can come back to it then if anyone remembers. Don't forget, there's also like midterm and the final, and many of those are like long answer written questions. So yeah, sounds convoluted. Nice. A+ on that pun. I see. Okay. I see a question from Piazza. Can we still use the combination formula when we are picking subsets with repeated items? For example, we select a subset of size 3 from 0, 1, 2, 2, 2. That is a really great question. And the answer is no. So what I'm going to do is erase this. So I'm going to draw a little table here. So we want care about order. Yes and no. And then can get same object twice. Again, yes and no. So we have this this chart here of like the 2 questions that you always want to ask yourself. So if we can get the same object twice, and we do care about the order, then we know we're going to use n choose k. So I'll just use a different color. Oh, sorry, not n choose k, n to the power of k. If we cannot get the same object twice, so then it's no, and we do care about the order, that's a permutation, so n to k factors. And if we can't, if we can get the same object, cannot get the same object twice, and do not care about the order, so the no case, that's the n choose k. So the question on Piazza was, what about this case? And the answer is we can't, there's not like a way to do it, because you need to know how many of each type there are. There's no like general formula. I mean, maybe there is, but not anything that we would have a notation for. And the example that was given was imagining selecting a subset of size 3 from 0, 1, 2, 2, 2. If we don't care about the order, then there's sort of different ways that we could do that. So we end up basically, I'll just write this example. So we have like 0, 1, 2, 2, 2. If we're choosing subsets from that, we could choose 0, 1, 2, and there's, I guess, 3 different ways to do that. Right? There's 3 ways to choose 0, 1, 2. We could pick 0, 1, 2, and there's 3 ways to do that, because we could choose the first 2, the second 2, or the third 2. We could pick 0, 2, 2. And, sorry, that looks like a 3. That's a 0, 2, 2. There's going to be 3 ways to do that, right? Because you could get 0 and the first and second 2, 0 and the first and third 2, or 0 and the second and third 2. So there's 3 ways to do that. Similarly for picking 1, 2, 2. If we're picking a subset, there's 3 ways to do that. But then, how many ways are there to get the subset 2, 2, 2? There's only one. There's only one way to do that. So we could do it. We could list out all of these possibilities, like here are all the possible subsets, but they're now no longer equally likely to occur. So you couldn't do anything regarding classical probability with a setup like this. The whole point, basically, of chapter 3 is to be able to count numbers of ways things can happen, so that we can use that classical definition for the numerator and the denominator. And in order for that to work, the outcomes need to be equally likely. But while these here, I'm going to change the color of ink again, these here are the possible subsets of this, if we don't care about the order, they're not equally likely anymore. So we couldn't use it as a denominator and then calculate a probability, because these 3 are, the top 3 are 3 times more likely than the bottom one. So hopefully that kind of answers the question as to why we can't really do that. Is it related? So yeah, it's kind of related to the multinomial coefficient. It's not quite the same thing, because with the multinomial coefficient, we are still looking at orderings. So we are caring about order rather than looking at numbers of subsets. But it's definitely related to that multinomial coefficient. It would be so nice if that just multinomial coefficient fit in that box there, but it really doesn't, because the multinomial coefficient is for when we do have repeated objects, so that part makes sense, but we do care about the order in those cases. Sorry, other way around. Multinomial coefficients, we don't get the same object twice. We do care about the order, but there are multiple objects that are indistinguishable from each other. So I guess in a way you could get the same object twice. It's just that there's 2 that are indistinguishable from each other. Another question. So 0, 1, 2 times 3, is that because there are 3 different 2's? Yes, exactly. Yeah, so like basically what you can do is like treat the 2's as like 2 sub 1, 2 sub 2, and 2 sub 3. Like give them names so they look different, and then figure that out. But yeah, that's the idea. Right. Okay, yeah, thank you for that question, whoever asked that on Piazza, and hopefully that explains it. So there isn't a notation for it, and we could, in an individual case, look at enumerating all of the possible subsets where we are allowed sort of repeated objects, but we don't care about the order, but they're not necessarily going to be equally likely, and so that runs into issues coming up with sort of a generic formula for it. Thank you for that question. Okay, I saw another question on Piazza. They just marked it as resolved. Great. If person B is 50% more likely to eat tacos than person A on any given day, and person A has an 80% chance of eating tacos on Friday night, what is the probability that person B will eat tacos on a Friday night? isn't it just, I'm not sure if I understand the question. So if person A has an 80% chance of eating tacos and person B is 50% more likely, you can't really be 50% more likely than something else, because then you run into the problem of having probabilities that are bigger than 1, and that's one of the axioms. That's like the second axiom, I think, of probability, that you can't have a probability bigger than 1. So I think the question as phrased doesn't really make sense. Like, I guess, yeah, what do you mean by 50% more likely? Do you mean like there's no way to be 50% more likely than something else unless the something else is guaranteed to be less than 50%? Because then you'd run up, or you'd end up with a probability bigger than 1. So hopefully that answers your question. There is no solution to that because the question is not valid as written. Unless there's something I'm missing. Okay. Okay, another question. So OOSS using multinomial coefficients gets 6 outcomes. Does that mean I treat each of the elements as distinguishable even if they're the same type? So the cool thing about that, yeah, assuming your letters are taken randomly to make 2-letter words. Okay, I'm going to erase this. Okay, so we have choose 2 letters in order from the set OOSS. And so that we're looking at how to do that. So one way to do it would be exactly like you said, sort of like consider that they're distinguishable. So call them like O1, O2, S1, and S2. Then there's going to be 24 possible 2-letter, sorry, not 24. There's going to be 4 times 3, so 12 possible words. So 4 to 2 factors, which is 12 words that you can make. But then the ones that have 2 of the same, they look 2 different ways. And the ones that have 1 of each, they each look they each look kind of 4 different ways. So I guess O1, O2 looks the same as O2, O1. So those really are 1. And same thing, like S1, S2 looks the same as S2, S1. So those ones are double counted. But the ones that involve 1 S and 1 O are actually quadruple counted, right? Like O1, S1 looks the same as O2, S1, which also looks the same as O1, S2, which also looks the same as O2, S2. So that's quadruple counted. And then same thing, like S1, O1 looks the same as each of those things. So I guess if we're talking about like how many different words can we make, there's only 4. But if we're talking about like the likelihood of each one, like these 2 are twice as likely as these 2, because if we're just picking them at random, that's what we end up with. So does that kind of make sense? There's 4 possible but they're not equally likely. And the only way to sort of figure that out, I guess, is to treat them as separate and then put them back together, I guess, into groups. If you were taking sort of like all of the letters and just arranging them into order, so like arrange the letters OOSS into a word, like a 4-letter word, then it would just be a binomial coefficient, a multinomial coefficient, because we would take the 4 letters, 4 factorial, and then divide by 2 factorial, 2 factorial, because there's 2 O's and there's 2 S's. The difference comes in this first case here because we're not using all of them. And so it depends which ones we pick, how many ways it can look. But if you're just talking about arranging those, oh no, I can't scroll down anymore. If you're arranging into a 4-letter word, then there's just 4 factorial divided by 2 factorial, 2 factorial, which is 6. And that'll be like, again, like OOSS, OSOS, OSSO, SSOO, SOSO, and SOOS. There we go. I got them all. So yeah, the difference is with those multinomial coefficients, we're always talking about that in the context of taking the entire set, including all the repeats, and arranging the entire set into an order. If we're selecting a subset and then doing anything with it, we got to be really, really careful. There's no notation for that. There's no like name for the terms or anything. And it depends on all of the exact details. But if you're taking the entire set, which includes some repeats, and arranging it into an ordering, that's where the multinomial coefficients come in. So hopefully that clarifies a little bit. Other questions? I'm going to check Piazza again because there were 2 great questions there. Oh, another one. Question 10 on a drawer contains 8 different pairs of socks. If 5 socks are taken at random and without replacement, compute the probability that there is at least 1 matching pair among these 5 socks. For each pair of socks, do the socks distinguish from each other? For example, if we get a pair of red socks, does the first red sock distinguish it from the second red sock? So this is an example where you could do the problem either way. You could do it basically treating this as left red and right red or something, and do it that way, or you can do it counting them as indistinguishable. So if you're going to draw, so you have sort of 8 pairs of socks, that means 16 socks, and each one has a match. So you can think about basically almost any problem, you can reduce it to picking a subset of letters or numbers, basically. So if you have imagine you have a drawer of socks and you have 2 A's, 2 B's, 2 C's, 2 D's, etc., 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 and we're going to select, what did they say, 5? Yeah, 5 from there. What's the probability that 2 of them are matching? So you'll want to take, basically, you could do it with like left and right for each pair, or you could just basically, you have different categories, and what's the probability to get 2 of any one category. I think it would be easier to do the complement in this case as well, to basically look at what is the probability that each of the 5 socks you get are drawn from different possible socks. So you could say like the first sock that you get, whatever, obviously is not going to be a match to anything. And then the second sock that you draw, there were 16 choices in the first one, so 16 choices for the first sock. For the second sock though, there's now only 14 choices because that you can't get the matching one. That would violate that. So I think using the complement might be a good way to approach that. Thanks for that question as well. Okay, so I will go for now. I'm going to put some of those great machine learning videos that someone mentioned at the beginning. I'll put those links onto Piazza because those seem really cool. I'll put the swag and machine learning idea of the week documents up on Learn in case you want to peruse those later at your leisure. And I will see you all next Friday. Just a reminder, don't forget today is the last day to create a group if you want to work with someone in particular for the collaborative assignment. So do that by midnight tonight. If you don't have a group, no problem at all. We will, once midnight rolls around, we'll make groups of anyone who doesn't have a group. So you'll have a group made for you, and then your TAs. Each TA is going to be responsible for a few groups, and they'll email you. They'll reach out to you probably over the weekend or maybe on Monday to get you started and make sure that you're all on track with the first collaborative assignment. But I'm really, really looking forward to seeing the questions that you come up with, and good luck on everything else that's going on in all your courses. And I will see you next time. Bye.